attempted to prove me wrong by typing in the chat. What do we have here? Johanna, yes, great. Okay, are you ready, Steffen?
Yes.
Okay, welcome everybody for the very last talk. I am pleased to introduce Steffen Lempp, who will speak on toward deciding the AE theory of the Sigma02 enumeration degrees.
Well, first of all, let me start with the customary things and the maybe not so customary apologies. So the customary things go to the organizers, Elvira, Paul, and Rod, for inviting me to speak here. As the last speaker of this conference, I should also thank everyone who was involved in this whole workshop. I've been able to watch part of it, but I'm sure it was a very nice conference, even the parts I didn't see. And so our thanks also go to the Institute and all the financial supporters of the Institute. The apologies is mostly for not being there. I would really have loved to attend in person. However, there is a small reason why I couldn't, and I'll reveal it at the end. That reason keeps me actually in New Jersey instead of in Cambridge. So part of the reason why I couldn't go to all the talks is because the internet was just too bad where I'm staying here. But hopefully that won't happen while I'm speaking here. So without further ado, let me jump into the talk. So deciding the AE theory for degree structures has been an obsession of mine for a very, very long time. For the Sigma02 degrees for at least 15 years. The results I want to talk about today, in particular, one result goes back to joint work with Iskander, Selvin, and Yamaleev. We started this during a visit of Selvin and myself in Kazan in 2014, put it aside for a very long time, and then last year realized that we really needed it for the AE theory, so we started again and finally finished it up with Iskander and Mars, of course. This ties in with another project, which I will briefly mention, that Maria reported on in Leeds last week. This is joint work of mine with Junle, Selvin, and Maria. So let's get started. So first of all, sort of as an outline, why would we even think about these kinds of questions? Well, most sort of natural degree structures that you come around to looking at in real life, quote unquote, are very complicated partial orders, and the pattern that they follow is usually the following. So the first order theory of this partial order is undecidable. I mean, it is just bad. It's, you know, it is not something really nice like the dense linear order or anything like that. In fact, this partial order is not just undecidable, it's usually as complicated as possible, which means as complicated as second order arithmetic for global degree structures or those of size continuum generally, or first order arithmetic in the case of countable, quote, local degree structures. So once you are faced with a situation like that, of course, as computability theorists, you want to know, well, where is the boundary? So people have been wondering, well, at what quantifier level does the undecidability start? So which fragments of first order theory are decidable, which are undecidable? And the boundary is generally always in the same place for all the usual degree structures. So the E theory is decidable. That's because all finite partial orders embed into any of the common degree structures. And so checking whether or not an extensional sentence is true in a degree structure is basically just checking whether or not it's consistent with the theory of finite partial orders. On the other hand, the AE theory can often be shown to be undecidable, for example, for the many 1 degrees, for the CE many 1 degrees, for Turing degrees, delta 02 Turing degrees, but not for many other degree structures, in particular not for the CE Turing degrees, and in particular also not for the Sigma02 degrees, which is enumeration degrees, which is a topic I want to talk about today. And then if you go one step further, if you look at the EAE theory, that can usually be shown to be undecidable. So therefore, that's where the sort of the wild country starts, and you know, you use some coding, and you can show it's undecidable. So Let me start just by reminding you what enumeration reducibility is. So A is enumeration reducible to B for two subsets A and B of omega if there's an enumeration operator phi, which reduces A to B. So that means that there is a CE set phi, which consists of pairs x comma f, where x is a number and f is a finite set coded by canonical index, such that for all x is in A if and only if the pair xf is in phi for some set capital F, which is a subset of B. So basically, this is like Turing reducibility, except you're only outputting positive information, you're only enumerating A, and you're only allowed to use positive information about B, which means from any enumeration of B, you're producing enumeration of A. So this is actually the uniform version and non-uniform version coincide by Selman's theorem, so it doesn't matter, but this is the easiest way to define it and the most intuitive for me anyway. So in particular, I'm going to focus on a local degree structure rather than looking at the global degree structure of all enumeration degrees. I will look at a degree structure which I call S sub E, which is the collection of enumeration degrees of Sigma02 sets, and that coincides actually by nice coincidence with enumeration degrees below 0 prime in the sense of the enumeration jump. So in some sense, these Sigma02 degrees form a counterpart of both the delta 02 degrees in the Turing world and the CE degrees in Turing world. And they share some of the properties of both, but they sort of lie in between, and they have some funny phenomena, which we'll see. The Sigma02 degrees form a densely ordered countable upper semilattice. So it's not just an ordering, but it's also a join. There's a join operation. And there's a least element, namely the degree consisting of all the CE sets. Remember, the CE sets are the ones which can be computed from any oracle. And there's a greatest element, which is the degree of the complement of the halting problem. So the problem with this enumeration reducibility, of course, is that it's not invariant on taking the complement. Right? If you take the complement, you generally get a different degree. So that the complement of the halting set codes the greatest element, the max. I mean, it encompasses all the, it can enumerate all the Sigma02 set in the sense of enumeration reducibility. So for SE, here's what's known. The E theory is decidable by a remark that was made by Lagemann in 1972, which is really based on work of Sachs's 10 years before, and an easy observation how one transfers results from the CE degrees to the Sigma02 degrees in some sense. The full EAE theory is undecidable by a result from my student Tom Kent's thesis from 2006. The full first order theory is as complicated as first order arithmetic. That was shown by Ganchev and Suskova in 2012, so only about 10 years ago. So we have the situation like I described in a sense, but the decidability of the AE theory remains open for the Sigma02 degrees. So let's look at that more carefully. So first of all, deciding the AE theory of the degree structure amounts to giving uniform decision procedure to the following algebraic problems. So remember, let me back up for a second. Remember that for the E theory, the reason it was decidable is that there was a very easy algebraic characterization, namely all you have to check is that all finite partial orders embed. The algebraic problem, the corresponding algebraic problem that corresponds to deciding the AE theory is a little more complicated, but it still can be stated fairly succinctly, and I'm trying to do that here. So we're given finite partial orders P and finally many, but arbitrarily finally many QIs, which extend the partial order P, call them QIs. And now we're asking, does every embedding of P into the degree structure extend to an embedding of QI into the degree structure for some I less than n, where the I may depend on the embedding. And we'll see some examples later on. So notice that this is a pretty easy problem to state, and you can show that this is actually true, that deciding for which P and QI, the answer is yes, is equivalent to deciding the AE theory. modulo disjunction, but disjunction is easy because it's just a finite number. You just have to assign this finite number of these kinds of problems. Okay, so there are two major subproblems in the AE theory which are known to be decidable. One of them is the extension Verbatix problem, and that's when you have only a single extension Q of P. So given partial orders P extended by Q, as every embedding of P into D extend to an embedding of Q into D for the degree structure SE? The answer is yes. It's a fairly complicated decision procedure based on a similar decision procedure for the CE Turing degrees by Slayman and Sohr from about 5 years before our solution. So our paper was published in 2005, but we worked on it quite a few years before, and it took a while to get published. It is a fairly complicated decision procedure. On the other hand, another subproblem, which is the following: which finite lattices can be embedded into D, preserving join and meet. Now, so this is not just an embedding as a partial order, but it's an embedding as a lattice, which means you want to preserve both join, which is kind of easy, but you also want to preserve meet, which is hard. And Andreas Sorby and I showed 20 years ago that indeed all finite lattices can be embedded into the Sigma02 degrees, in fact, even preserving 0 and 1. So those subproblems are known to be decidable. The main obstacles for the CE Turing degrees in deciding the extension Verbatix problem were one was a lattice theoretic, and one was what's called saturation kind of property. For the Sigma02 degrees, there's a third phenomenon cropping up, and this was first found, well, an instance of this was first found by Ahmad in her 1989 thesis. This was later published in a joint paper with Lachlan, her advisor. So let me quickly mention this. So there's an Ahmad pair of Sigma02 degrees, A and B, such that these are incomparable. So Ahmad pair means that A and B are incomparable Sigma02 degrees, but A degree strictly below A is less or equal B. So basically, the degrees below A just come in two flavors. Either you're equal to A or you're less or equal B. So that's kind of a weird, strange phenomenon. Particularly notice that this means that A is a non-splittable. It is Turing irreducible, right, in the Sigma02 degrees. On the other hand, she showed that this phenomenon cannot be made symmetric. So there's no symmetric Ahmad pair of Sigma02 degrees. Namely, you cannot find Sigma02 degrees A and B such that any degree strictly below A is less or equal B, and conversely, any degree strictly below B is less or equal A. So here's a little picture. I wanted to illustrate how this fits into the framework of deciding the AE theory. So here the AE statements, which are blocked or not blocked, which are blocked for P and extended to Q0. So that's the middle and left picture. So P is just the antichain AB, and Q0 puts one element below A, which I'll call V, and it does not put V below B. That can be blocked. On the other hand, you cannot simultaneously block and extend an embedding of P being extended to either Q0 or Q1. So that's what the second half, the no symmetric Ahmad pair says, that either I can find a V below A, which is not below B, or I can find a W below B, which is not below A. So that's sort of the starting point of this investigation, because this seems to be the hardest aspect of the whole problem. About 15 years ago, Kent emailed me the following, what he called the next two questions arising from Ahmad's work. And he really did phrase it. I mean, it was actually a longer email. It was like about 3-page PDF file. But the main two questions he said are the following. First of all, is there what he called an Ahmad triple of Sigma02 degrees? Namely, are there pairs A, B, C, so that AB forms an Ahmad pair and BC form an Ahmad pair. So of course, remember what that means. That means that anything strictly below A has to be less or equal B, and anything strictly below B has to be less or equal C. That's question one. And question 2, is there a cupping Ahmad pair? Namely, is there an Ahmad pair AB such that A join B is 0 prime? So it joins up all the way to the top. So these are the questions that in the middle of the first decade of this century were the main questions that were open, and they were the obstacles to going from just the extension Verbatix problem to deciding the full AE theory. So let me just show you the picture, for example, for one, just to see how this fits in there. So for one, having an Ahmad triple would mean that I can block an extension, that I can find an embedding of P and block at the same time any extension to Q0, Q1, Q2, Q3. And you can amuse yourself by just looking at it, right? So Q0, for example, says I can put something only below A. Q1 says I can put something below A and C, but not B. So that together, Q0 and Q1 say that A and B form an Ahmad pair, of course. And similarly with Q2 and Q3 says that BC form an Ahmad pair. Because you have to have 4 things because you have to fully specify the partial order in the QI. So for many years, I thought that the answer to both of these questions was yes. In fact, I am somewhat embarrassed to admit that when I gave a talk at in the very building that you're sitting right now, 10 years ago at the February workshop during the Turing year, I claimed in a talk that I could show that there was an Ahmad triple. Unfortunately, that turned out to be false. And I now know better. And in fact, we have a paper which we have already submitted. It's on our websites. So this is the joint work with Junle, Selvin, and Maria. There is actually no Ahmad triple sigma 2e degrees. The way we had to prove this in a nutshell is to analyze very carefully Ahmad's proof that there is no symmetric Ahmad pair. Her proof is sort of non-uniform it's split into 2 parts, and they're kind of technical. This sort of kind of technical interface, and that really confused us for a very long time. So it was I think mostly Selvin's insight to see how to write up the no symmetric Ahmad pair in a way that was sort of a direct construction. And once we had that, we were then able to show that using one more layer of non-uniformity, one can actually show there's no Ahmad triple. So this was so there's actually 3 layers of non-uniform. Well, it is doubly non-uniform, the construction. What you do is you first show a counterexample. You try for a counterexample for Ahmad AB being an Ahmad pair. If that fails, use that failure to try to show that BC is not an Ahmad pair. Failure of that, you go back to AB and show that there is yet another possible failure of AB being an Ahmad pair, and one of these 3 strategies will succeed. So that's the first half of our paper. There was sort of a companion result. There is what we call a weak Ahmad triple, namely there are pairwise incomparable sigma 2e degrees ABC, such that AB and AC do not form Ahmad pairs. But if I look at the degrees strictly below A, then each such degree is either less than or equal B or less than or equal C. So none of them, it's not true that all of them are below only B or only C, but together, if I look at basically principal ideals below B and C, they exhaust all the degrees strictly below A. So we thought that was kind of an unusual phenomenon, sort of a companion result to show no Ahmad triple. This led to some exciting ongoing work which Maria will report on last week in Leeds. I will just give a very brief summary if I have time, but let me show you the other theorem which is the focus for today. This is the work with Iskander, Selvin, and Mars. Now, I finished the proof only a couple weeks ago, writing it out. So if it's wrong, then it's my fault. And if it's right, it goes to all our credit. So the result there is that there's no cupping Ahmad pair, namely given any Ahmad pair, you can show that A join B is not 0 prime. All right, so those are the two results I wanted to mention. Well, the two theories. So I want to mainly focus in when I sketch the proof on the second one, but the first one I want to just take a little more time to explain the context. So, given the difficulty of the overall problem of deciding the A theory, I mean, people have, myself included, have been concentrating on the following subproblem. And rather than looking at all partial orders P and all possible QIs, we're looking at finite antichains P and one point extension Q. And the 1 point extension Q is only allowed to put a new point either below one of the AIs or one or several of the AIs, or put a point below above one or several of the AIs. So we call this Q sub S. So XS is a new element, which is exactly below the AIs, such as I is an S for any non-empty subset S of the interval 0, n. And T means that X super T is a new element, which sits exactly above the AIs for which I is in T for some arbitrary non-empty subset T from 0 to n. Now you might wonder, why am I saying that S and T have to be, actually, hold on, before I go on, let me just, okay, so now the same decision procedure. Now the question is, does any embedding of P extend to an embedding of some QS or some QT in some given list of possible S and T? So obviously, the fewer S and the fewer T you allow, the harder the problems becomes. So this is downward closed for being blockable, and upward closed for being realizable, right? So this is the basic setup that we obviously have to solve first before we can solve the rest of it. This has already seemed hard enough. Let me point out that it's always possible to extend an n+1 element antichain by adding one more element to the antichain, right? You can always, given n+1 many degrees, a0 through an, you can always find another degree to the side. So that's a boring case, right? So we didn't want to consider that case, which is why I didn't mention it. So the interesting part is just whether you can put stuff below certain AIs or above or below certain AIs. All right, so with Selvin, Junle, and Maria, we formulated working conjecture for the above subproblem, but only looking at the Q sub S, because that's already hard enough, because we didn't actually have we were not looking at the Q super T yet, because that other result about copying Ahmad pair, which obviously is some subproblem, well, if you combine above and below, was very recent. And so our working conjecture involves basically generalizing the fact that there's no Ahmad triple, there are Ahmad pairs, there's no Ahmad triples, some other extension of Ahmad pairs, and then a bunch of minimal pair questions like, can you combine Ahmad pair and minimal pairs construction in various ways? So that's the context that we wanted to look at. And the precise working conjecture is the following. So so this is looks a little daunting. Fix an n greater than 1. Okay, so we want to have at least 3 elements in our antichain, and look at a collection script S of non-empty subsets of 0 through n. And now that means I now have a number of sets, and I want to know, can I extend every embedding of P to an embedding of Q sub S for some S in script S, right? That is a technical question from the slide before. Let me show you the slide before one more time, right? So here was the question. So forget the Q super T for a minute. Just look at the first half. P consists of A0 through AN, and then Q sub S adds one X sub S, which is an element which sits precisely below the AI for I and S for certain sets capital S. And these certain sets capital S are precisely captured in this collection of script S. Okay, so the script S determines which sets capital S are allowed. Now, I can partition 0 through n into two pieces. S0 is the part, is a collection of I, such as singleton I is the script S, and S1 is the rest. And we'll see why this is important. It's an important partition because our working injection, we have one direction already, and I'll say how close we are on the other side. So an embedding of P into the sigma-2 degrees cannot be extended, so can be blocked from being extended to any embedding of QS for any S in script S, if and only if two conditions hold. Well, either S0 is empty, namely there are no singletons, or S1 is empty, namely that every singleton is in there. Every singleton is in there. Or the second part is there is an assignment, as we call it, which is a function from S0, which remember has to be now a non-empty set, because we're assuming that the first pool does not hold, into the powers of S1. Again, powers of S1 is non-empty because we're assuming S1 is non-empty, minus the empty set. So therefore, we're looking at a function which maps every element in S0 to a subset of the non-empty subset of S1. And we have the following properties. All you need is that the function respects that for any I in S0, for any argument in the domain of this function nu, singleton I union nu I is not in script S. And secondly, if I take any non-empty, in fact, any subset capital F of S0, which has at least two elements, then the intersection of the nu I, which is the images under this function, is also not in script S. Okay, so this is our current conjecture. At the moment, we can prove left to right, which means we can prove that the embedding can be blocked, implies that S0, either S0 is empty or S1 is empty, or there is some assignment satisfying these properties. The other direction, we have some special cases, but it involves a whole bunch of cases. I mean, it's a priority construction at the 0 triple prime level with about eight kinds of different requirements and so on. So obviously, this is going to take us a while to write up. We are reasonably confident we're going to be able to finish this at some point, but it is not easy. We don't currently have a working conjecture yet, which also talks about the Q super T. So these are the one-point extensions which put new elements, one new element above some of the AIs. Because this result about the no copying Ahmad pair is a very recent result that we haven't really talked about haven't really talked as a group yet. In fact, it's not public yet. I mean, because we haven't really finished the paper. I mean, we've kind of finished the proof, but we need to put some finishing touches on it still. All right, so I guess I'm running a little early with the time, but that's okay, I guess, because you guys the last talk, so nobody's gonna complain about leaving early. Let me conclude by sketching the proof of why there is no copying Ahmad pair. So the proof is actually a finite-injury argument, believe it or not, but it's non-uniform. And it's also kind of an unusual format because what we're doing a weak splitting argument. So suppose I have two sigma02 sets A and B, and suppose that they form an Ahmad pair, and in fact a cupping Ahmad pair. Then I'm going to do the following. I'm going to, first of all, since they cup, I know that there must be a reduction from A join B to K bar, which is a representative to degree 0 prime. So let's fix that lambda. So I'm given A, B, and lambda. And now I'm going to build x0 and x1 reducible to A, as well as the enumeration operator gamma, such that the following requirements hold. So there's one global requirement, which says that A can be reduced to B join x0 join x1, So that's where the weak splitting comes in, because what it says is the global requirement together with that x0 and x1 are below A say that x0 join x1 is equal to A modulo B, right? So if I join everything with B, then they're the same degree. So A can be split into non-trivially into x0 and x1 modulo B. That's what the global requirement and the x0 and x1 below A say. And then we have these n requirements, as we call them. So these are negative requirements which restrain things. And what they do is they say, well, we also don't want that A can be computed either from x0 or x1, because if, for example, if A can be computed from x0, then actually I can find an enumeration operator omega. This local strategy will be able to find a enumeration operator omega such that A is reducible to omega of B. So is equal to omega to B of B. And similarly for x1. So that means in particular, suppose now the degrees of A and B form an Ahmad pair, then we show a contradiction. If they were to form an Ahmad pair, then the n requirements would ensure that x0 and x1 are strictly below A, because if one of them is not strictly below A, then because of the setup, we would have that A and xi, some xi, would have the same degree. But then, of course, we have that A is below B, and that is not allowed under Ahmad pair, because Ahmad pair means that 2 degrees have to be incomparable. Therefore, we have from the n requirements that x0 and x1 are both strictly below A. But then, since we have an Ahmad pair, that means that x0 join x1 is also strictly below. That means that x0 by Ahmad pair, we know that x0 and x1 individually are below B. Therefore, the join of x0 and x1 is also below B. But if x0 and x1 is below B, then because of the global requirement, A is below B join x0 join x1, and that's a contradiction because obviously if x0 join x1 is below B, then that means that A is below B. Again, a contradiction to A and B being incomparable. Okay, so this is the idea behind the whole thing. Now, obviously, this is not your usual finite-injury argument. I mean, there are a few sort of subtle points. So let me just mention a few of these subtle points. So I put at the very top of the board the global requirement, the requirements again, just to remind you. So we have the global requirement, recall that A is gamma of B join x0 join x1. And we have these local requirements n super I. If A is below xi, then actually A is below B, right? Those are the types of requirements we have to ensure. So what are the strategies? Well, first of all, how we're going to ensure the global strategy. So global strategy puts markers into the xi with the use. Remember the use. I mean, remember the reduction gamma is really just a. I mean, the reduction of xi to A is a pair x comma f. So the x in our case is a CIA. So for I is equals 0 or 1. So I'm putting the number, the coding location C into xi exactly when little a is in capital A. And I do it on both sides. I'm putting C0 into x0 and C1 into x1 exactly when A is in capital A. And then I define conversely the gamma reduction by saying that little a is in gamma of B join x0 join x1 with the use which includes in the xi use the ci sub A as one of the things, except there would be other things too. I mean, the pure strategy would just say that I just need those 2 elements, but actually we'll see we need a bunch of stuff later on too, which makes this more complicated. So that's sort of the global strategy, which is trying to define the enumeration operator gamma, right? So the gamma, recall, is just when we see little a enter a capital A, we define CIA and we put CIA into xi, And then we say, okay, so the CIA is going to be in XI if and only if little a is in capital A. That's what the strategy is. And now we have the obvious enumeration operators. That's the pure global strategy. So how does the NI strategy work? That's a little more subtle. So an NI strategy does the following. So the hard part is to keep the NI strategy finitary, because we promised that this was going to be a finite-injury argument. Well, it's a finite-injury argument unless, of course, somebody can show that A is below B. So as soon as we can show that A will run, we don't have to worry about the finite-injury anymore. But it's sort of like, so it's finite-injury in a Sachs of in the sense of Sachs splitting, right? So in the sense of Sachs splitting, we have that. If the hypothesis theorem holds, then it's really finite-injury. But there's no computable bound on the finite-injury, just like in Sachs splitting. So what does the NI strategy do? It says, okay, let's look for the oldest A, so that the little a that has been around for the longest time in both capital A and in delta with some finite set capital F. And I don't care whether capital F is a subset of X anymore. I'm just searching for any capital F whatsoever, any finite set whatsoever. And what I'm going to do is I'm going to dump this capital F unconditionally into Xi. So basically, I'm putting every element of capital F into Xi without worrying whether or not a corresponding element is in capital A. So obviously this contradicts the global strategy. Global strategy is very careful in saying you can only put little c into Xi if a corresponding little a goes to capital A. The NI strategy is very blunt. It just says, just dump the whole set capital F into Xi and don't worry about things. Of course, if I dump capital F into Xi, that will ensure that little I is now in delta Xi forever. When that happens, I'm going to declare little a to be confirmed, because it's now confirmed to be at least delta Xi. And if it's not in A, well, that's the opponent's problem. Because then basically I've been able to diagonalize, and then we have to sort of turn off the coding eventually. Now, to prevent infinite action, we're now going to use the fact that we have a copying Ahmad pair. So we're going to use the recursion theorem, which tells us that there is a part of the halting problem that we control. So we're going to define an agitator, little pa, which is a new number, and we keep that pa out of k so far, which means it's an element of k bar. But since it's an element of k bar, recall that means, let me go back for a second here. Look at the assumption in line 4 of this page. If little pa is in k bar, that means it must be lambda of A join B. So that means, let me go back here. So that means when I, oops, hold on a second. Where am I? Oh, here, right. Yeah. So prevent infinite action, I'm going to choose this agitator little p sub A, which is k bar. Therefore, it must be lambda A join B. And say the use of this of this lambda reduction is some finite set f sub A and some finite set g sub A joined together. So if f sub A is a subset of A and g sub A is a subset of B. And I wait furthermore until all the A prime and f sub A are confirmed in the sense of the first sentence of this paragraph. When that happens, then I'm going to define my omega by saying little a is an omega of B join X0 join X1 with a B use GA, and with the XI use is the set of all CIA prime where A prime corresponds to the finally many elements which are in F sub A. Okay, that's a somewhat delicate reduction because notice also that, by the way, this allows us, of course, to still correct omega as long as there's not too much dumping going on, because as long as I can remove either C0 or C1 for little a prime, I can remove little a from omega, right? This is the idea behind this, unless, of course, GA is not a subset of B, in which case I'm also happy. So this is the technique how to prevent infinite action. So the technique is then if I ever from now on see little a leave capital A, then I'm going to enumerate little PA into K. But now if PA enters K, that means it leaves K bar, which means that either FA can that either the XI use either FA is not a subset of A or GA is not a subset of B. If GA is not a subset of B, great, because then we're basically done. So we stop whenever we see that PA is in K already and GA is in B, because now we know that FA is not a subset of capital A. But if FA is not a subset of capital A, since FA is confirmed, all elements of FA are confirmed, that means FA is a subset of delta Xi. Therefore, we've actually diagonalized A against delta Xi. On the other hand, when we enumerate PA into K, we're going to choose a new agitator. Let's call it P prime A if A re-enters A. Remember, A is a sigma 2 set, so there are two possibilities for little a. Either it infinitely often goes in and out of capital A, basically, right? I mean, of course, it could also just stay out of capital A forever, which that's the easy case. The hard cases are little a either eventually is always in capital A, in which case stabilizes, the agitator stabilizes it, it's going to be an agitator which is in K bar, or infinitely often the element enters and then leaves capital A, in which case I keep enumerating agitators and keep choosing new agitators. No agitator is stable, and therefore I will never have a stable omega axiom, which means I will actually have this reduction correct. Now, of course, I have to make sure that this is still under finite, finite action, but so far it looks okay, right? I mean, we just one requirement. Now the problem comes up in the case when I have two requirements. So again, I put the requirements top of the board just so you can refer to them. So the conflicts are that if an N0 strategy, let's say it's a higher priority strategy, dumps C0A into X0, and then later on an N1 strategy dumps C1A into X1, for the same little a, then the global strategy can no longer undo the fact that little a is in gamma. Because if now little a leaves capital A, then it's no longer ensured that either C0A leaves X0 or C1A leaves X1. So that's a problem. So that's the main difficulty in this whole argument. And the way we're going to address this is the following. We're going to use yet another type of agitator. So the higher priority N0 strategy will choose an agitator Q, which again is going to be by recursion theorem chosen by us, and we can enumerate whenever we want to. Again, it's a recursion theorem with parameters as usual. And also a large threshold, which is basically any number bigger than R. Whenever the priority, the higher priority N0 strategy acts, it will choose agitator and then enumerate this agitator into K every time it acts, and then choose a new agitator and a new threshold. Now, since we're assuming the higher priority N0 strategy acts only finally often, eventually there will be a stable agitator Q whatever how many primes, which is really in K bar, and this strategy will shut off, and also there will be not a new threshold. The threshold is just basically restrained, which says that N1 strategy is not allowed to do anything below that threshold. Okay, so that N0 strategy is fine with all that, right? Because I mean, basically all it does is it just kills the N1 strategy for a little bit. How does the N1 strategy work? So let's assume the N1 strategy is lower priority. So the N1 strategy actually comes in 2 to the R many flavors. Namely, for every initial segment A restricted to R, let's call little sigma, it has a different strategy. So the hard part in this strategy is to show that even though I have like 2 to the R many different N1 strategies, all trying to guess A restricted to R in different ways and then work in their own way, no matter whether or not the little sigma, which is a guess of the sub-strategy, has the correct guess about A restricted to R or not, it's still going to be finitary. That's the hard part. And the way it works is that this N1 strategy initialized every time the N0 strategy acts, which means you start again from fresh, where you throw away your omega, your version of omega, and so on. Also, the N1 strategy is not allowed to dump anything into X1 restricted to R. That means that but remember that the N0 strategy will only dump numbers into X0, which are less than R, and therefore have to come from arguments which are in capital A restricted to R. Anything bigger than little r is not going to be related to anything that the N0 strategy dumps. So that's how I keep them apart. Now also the N1 strategy is allowed to freely dump into X1 but only numbers greater than or equal R, but only but it doesn't unconditionally dump it, but it only dumps it in a way such that when Q enters K, then this dumping is undone, because now Q entering K forces either an A or a B change, and that will force a lambda correction, and a lambda correction forces an H or an B change, and that will undo my omega axiom, and also ensures in the end, after somewhat complicated two or three page argument, it shows that the strategy is still finitary. All right, so I think I hope I have conveyed the gist of the proof. It really is just a finite-injury argument, but of course it is a highly non-uniform finite-injury argument, because you can imagine that with just two strategies you already get this high level non-uniformity. Of course, it's going to get worse as you add more strategy, but the basic ideas are really captured in these three slides. Okay, so that's all I want to say. So first of all, thanks for listening, coming to my talk. Sorry I could not attend in person, but there is actually a reason, and the reason is this guy, my grandson, born 1 week ago in New Jersey. Thanks.
Thank you. First question is, what is the name of the grandson?
Sebastian.
Sebastian, cool. Any other questions? Question from Ted. Let me walk the mic over there.
Hi, Steffen.
Hey.
On different occasions when I looked at these fragments of theories of degree structures, one thing that sort of made me stall out and eventually give up was that I couldn't seem to be able to find a way to work both sides of the problem. So that the decision procedures became more and more complicated, but they didn't inform me as to a phenomena that might lead to undecidability, down at the two quantifier level. Have you seen anything emerge that would let you, that give you a hint that you could work the other side of the problem too and prove some undecidability theorem?
No, so far I at least, I can't speak from all my co-authors, but I at least do not see any way to prove undecidability. I think that in the my conjecture is that in the end we will be able to show undecidability. Maybe not in my lifetime, but eventually it will be able to show it. However, this procedure is going to be really, really complicated. It's already complicated just for putting one single point below an antichain, right? in the various combinations. But so far, every time we looked at particular problems, we were eventually able to figure it out. And eventually the pattern sort of fell in place. And I have sort of a first conjecture about the other half with the Q super T and so on. Now, of course, once you have that, now of course you got to worry about multi-point extensions, say of antichains, and then you got to worry about what happens if capital P is no longer just the antichain but an arbitrary. But anything I've seen so far doesn't really point to undecidability. It just points toward a really, really horrible decision procedure.
Great, thanks. So in the end, you believe it's going to be decidable? Is that right?
In the limit,
In the limit.
without modulus function.
Very good. Any other questions? What's the story for the AE theory of the full enumeration degrees?
It is also open, and in fact, Maria, Ted, and I were able to show recently that the extension of embeddings problem, which is this problem right here. Let me pause, go back to that for a second, just to show you. Hold on, let me go back. Yeah, so look at the middle box, right? So extension of embeddings problem is this problem extending a finite partial order P to a single partial order Q. We were only a year ago able to give a decision procedure for this problem, and the decision procedure is also quite hard. Just like for the Sigma02 degrees, it was hard when we did it back in 2005. Maria, Ted, and I were able to show there is also for the global structure a decision procedure. It is different. It is different because the global E degrees are not dense. They're downward dense, but they're not dense. So in fact, you can embed into the pi02 E degrees any finite distributive lattice in a very strong sense, such that to embed the lattice with the top element A and the bottom element B, such that any element less than or equal A is either in the range it is embedding for finally many points, or is strictly less than B. So that's one of the key ingredients of our decision procedure. Of course, there are a whole bunch of other ingredients involving genericity and so on. So to show how can extend. But the main blocking mechanism is this result where we embed this finite distributive lattice in a way so that it forms an interval in a finite interval in the global enumeration degrees. I'm a little less hopeful about finding deciding the full AE theory there, because I simply don't know yet enough about this thing. I mean, again, we're hoping to get back to this. It might be easier because there's no Ahmad-like phenomenon, but there are other obstacles like the non-density. But maybe the non-density makes it easier. I'm not totally clear. Maybe Ted has a conjecture about this which differs from mine, but my guess again is that in the end it's going to be decidable. But I have less of a feeling for how that goes because I've just worked less on it. I've only worked on that for the last couple of years.
Great, thanks. Anything else? Online, friends? Oh, Selwyn. Okay, great. Go ahead, Selwyn.
Yeah, so for the global E degrees, did you think about the things like one-point extensions? Does that make sense? That's the second question.
We haven't really thought about that carefully with the one-point extension, because I mean the one-point extension was inspired by this Ahmad phenomenon, which is not really present in the so the Ahmad phenomenon is sort of a weird phenomenon because on the one hand you have a dense partial order, on the other hand you have this Ahmad phenomenon, which is a very special thing. So that's what inspired us to look at the one-point extensions. For the global enumeration degree, since you have intervals which are finite distributive lattices, and maybe even arbitrary finite lattices, this is the next thing we're going to look at. Maybe we can embed arbitrary finite lattices into it. That's our next hope. And then, so we're hoping that we can mimic. So let me back up for a second. The way that decidability for the Turing degrees and for the delta zero Turing degrees was shown for the AE theory was for the Turing degrees, it was shown by basically it's based on Lachlan, who showed that there is initial for any finite lattice, there is an initial segment of the Turing degrees which is isomorphic to it, and now you have to just show that that okay, so now extend the P in the minimal way to a finite lattice, and then show that you can basically realize anything which does not violate putting a new point below an old point, in some sense. That very roughly speaking, for the sigma2, as for delta 02 Turing degrees, it's a somewhat different proof, but it's basically the same proof, except that all the elements except for one is mapped to an initial segment, and then any maximal elements below one cup to 0 prime, and so you're blocking a whole bunch of extensions. So that together with the initial segment result, where you just embed as the last initial segment, allows you to give it precision sigma to degrees. My hope is that something like that could be made to work for the global enumeration degrees, except that you can't do it as initial segment because it's downward dense, but you can sort of go by going up into the pi02e degrees into some interval. And now you have to, of course, carefully analyze what happens below, what happens above. Although there are some obstacles, we had some conjectures. One of the conjectures was actually shot down by a Maria student, Jacobson Grocott, almost immediately, unfortunately. But we just haven't thought long enough to really figure out. I'm not sure the 1 point extension is really quite the right way to approach it. I think it's more that you want to sort of analyze, what things can be blocked by intervals.
Okay, but you're saying you have a decision procedure for all possible 1 point extensions. So,
for 1 point extensions, hold on a second, let me think. Not simultaneously, although my guess is that we can probably soup up our argument for the extension of embeddings problem to a decision procedure for 1 point extensions. It's my guess.
Steffen, I think that problem is probably tied to the question of whether every lattice can be embedded as a strong interval.
Possibly. I'm not sure. Yeah, I mean, anyway, I don't think it's that far away, but I mean, yeah, this is definitely something that we will counter on the way, but it doesn't seem to be as much of an obstacle just looking at 1 point extension. I think it's more looking at intervals. I mean, it's just a different flavor of structure as far as I'm concerned. Yeah, but that's right. I mean, we have to check all finite lattices, not just finite distributive lattices, but overall, my hope is that we can avoid this horrible 1 point extension analysis for the global E degrees. It's a different animal, so I think a different approach is needed there.
okay.
That's a good question.
Okay, anything else? Yeah, let's thank you. Yeah, great.